Welcome to the field here in Eastern Arkansas. This is our third virtual field trip series in the Soil and Water Conservation Series funded by USDA's Natural Resource Conservation Service. So in this third series of our virtual field day, we're going to talk about things that we're seeing in the field, the ins and outs of the sampling process on the discovery farms, and what we're seeing specifically on farms. So to talk more about the sampling process and the ins and outs of how that works, we're going to turn it over to Lee Riley. So Lee?
Thanks, Matt. Hopefully you were able to join us this morning, so you've already got a pretty good idea of what the Arkansas Discovery Farms program is. And if you were able to join us this morning, you saw this box behind us that we had closed up. Well, today we're going to reveal what's in the box, what we use to capture edge-of-field runoff. Just short and simple, in the Arkansas Discovery Farms program, we are analyzing edge-of-field runoff on real working farms. So we are collecting data on nutrient and sediment loss or solid loss off of fields. To accomplish that, we use some sophisticated instrumentation. If you'll take a look at this image right here, this is what a typical edge-of-field site looks like. The box you see there houses the instrumentation. The pole there in the foreground with the solar panel keeps the 12-volt batteries that power the system charged. And at the top of that pole is a rain gauge. And so that rain gauge allows us to know how much rain has fallen on the farm. So we are monitoring literally all the water that comes on the farm and all the water that runs off of the farm. So with the rain gauge like you see there, and the flow meter like you'll see in this next image, the flow meters on wells allow us to know the amount of water that's used for irrigation that's put on the farm. So we know all of the input and all of the loss on the farm. So the instrumentation we use, like you'll see behind me here, are ISCO 6712 water samplers. These are automated water samplers, programmable to take water samples when we tell them to take a sample. We're taking a composite sample up to 10 liters. So we've got 100 milliliter samples that can give us a total volume of 10 liters. And if you'll take a look at this next image, what you see here is what we see as a graphical representation of a runoff event. This software is Flowlink. You're going to hear a little bit more about that from Pearl in a little short while. But if you take a look at this image, you'll notice that graph is sort of bell-shaped. It's a little lopsided, but this is a hydrograph. This shows us the water, a runoff event. So if you'll think about how rainfall happens, it starts gradually. We get sprinkles normally. Rainfall develops a little more stronger precipitation and then tapers off. So our goal is to capture a snapshot of that entire event. And if you'll take a look at the triangles that are under the graph, each one of those little triangles represent a sample that's taken. So we want a composite sample of an entire runoff event. So we are setting these samplers to take a sample based on volume that's leaving the field, normally in gallons, through what we call flow pacing. So the flow pacing is how often that sampler takes a sample throughout that irrigation event. So how often those samples happen under that curve that you're seeing there. So we are triggering those events to happen a couple of different ways. In the next slide here, you'll see an area velocity meter. That area velocity meter, I have one here in my hand as well. That area velocity meter tells the sampler how much the depth of water is based on pressure, as well as uses a little Doppler radar signal to give us a velocity based upon particulate matter that's flowing off of the field. So we use these typically in pipe like you're seeing there, and I think this next image is also a pipe. So if we're monitoring runoff in a culvert, pipe, flashboard riser, this is how we're going to trigger the sampler. Now, we don't always have the opportunity to monitor a pipe. Oftentimes our farms have open channels, ditches, tailwater tailwater ditches, irrigation canals. So to monitor the open channel flow, we use a different sensor. Those sensors are similar to the area velocity meters. These are pressure transducer. This is not as fancy of a sensor. This only tells us the pressure of the water, and then based upon what this pressure tells us, the sampler can then interpolate depth. So when we are monitoring an open channel flow, we're going to install a flume in that channel. That flume gives us a constant geometry, a known geometry of a channel. So if you think about a typical ditch, water flowing through it, the channel's never going to be in the same spot. Occasionally the channel might get wider, it might get deeper, or it could fill in with sediment, it could silt in. So we need to be able to have a controlled geometry of that channel. So I believe you're seeing an image of a flume, or may have already seen the image of the flume. So those flumes are how we do that. So we know the geometry of that flume. We know the depth of the water thanks to the pressure transducer. So with this equation, you'll see on this next image. So this is the equation that we'll put into the sampler. So the sampler will be able to then calculate and tell us velocity and volume. And then we communicate with our edge of field monitoring equipment with cellular modems. This here is a cellular modem. It's got a magnetic antenna similar to what you would have on a automobile if you're going to put an external antenna on your car. And that sampler, or that modem, allows us to know if a program has enabled, if the program's done, if we have errors. It also allows us to communicate and download data with that Flowlink software that you saw earlier. You may be seeing an image on the screen here. This is showing a message that the program is done. So when the program is done, we'll get a text message. We can also communicate remotely with anywhere we have a internet connection and have that software. So that's really beneficial to us because we're monitoring rainfall and irrigation runoff. So my office is in Little Rock, and we've got discovery farms all over the state. So if it's raining in Cherry Valley or Helena or Dumas, and I'm in Little Rock and it's not raining, and I get a text message from one of our stations there that says the program's enabled, I can then know that it's raining there. I'll normally pull up the weather radar and check things out. If I get notification from one of those sites and weather radar doesn't show it's raining, and depending on the time of year, I normally know that a farmer is in irrigating, so I know that expect that I've got irrigation samples. So I mentioned that we're taking a composite sample up to 10 liters throughout each of those runoff events. We're going to then take that composite sample, and we're going to break that down into subsamples. In this image, you see one of our program technicians, Michael Freyaldenhoven, is taking subsamples. So there we are pouring the 10-liter jug into subsamples. Those subsamples are going to be shipped to the Water Resource Center in Fayetteville, where they are analyzed for nutrients. In this image, you will see what those subsamples look like. We have subsamples that are tested for total nitrogen and total phosphorus. Those samples are treated with sulfuric acid. That is to stop biological activity in the samples, so nothing is breaking down those nutrients. we're going to test for total solid loss. And then you see a syringe and those round discs in the foreground. Those are syringe filters. We are filtering samples at 0.45 microns. That's pretty small. Though that's going to remove any of the solids from the sample so that we can then test for the dissolved phosphorus and potassium. So we need to get the soil out of the sample so the phosphorus in the sample doesn't have opportunity to bind with the soil that is in that sample, and that'll give us the ortho phosphorus, the water-soluble phosphorus that's in that subsample. And once we get the results from the lab, we normally get data back in about 6 weeks, sometimes shorter. Then we are able to analyze the data and figure out what we need to do from there. That data will go into reports, and Pearl is going to talk to you about that in a little bit later. I really appreciate your time. Thanks for joining us this morning.
Thanks, Lee. We really appreciate your time talking to us. Next up, we'll have Pearl Webb speak to us. She's a program associate that works with Lee and Dr. Mike Daniels in the Discovery Farm program, and she's really kind of the brains and the analyst behind all the data. She puts it all together where we can all digest it. So she'll walk you through the process that she takes to get that done. So Pearl.
Thanks, Matt. So I'm going to be talking about how we obtain the data that we've collected and put it into a usable format. It all starts with the program Flowlink, as Lee had mentioned. Flowlink is the software that ISCO developed to download and interpret the data from the samplers. So the data can be downloaded remotely using the cellular modem from the field. This is what it looks like within Flowlink when you're connected to a station. This is DUMIS 4. And while you're connected, you can view the real-time measurement data. This next image shows what it looks like when I'm actually retrieving the data from the sampler. This is also the DUMIS 4 station. And Flowlink uses built-in equations such as Manning's equation to calculate things such as the flow rate and the volume of a particular event. So certain parameters of those equations are site-specific, so they're built into the station's programming, and that includes the pipe or channel radius, the roughness coefficient, and the slope. And then the variables of level or velocity are provided by the sampler instruments that Lee showed you, which are the pressure transducer or the area velocity meter. So within Flowlink, this is a dialog when I'm doing a flow conversion. From here I can change the units, and I've selected DUMIS 1 for this station, and so it enters those pre-programmed parameters for that site. The volume conversion is very similar. I'm actually using the flow that I just calculated previously to determine the volume for this station. Flowlink can also create hydrographs of the runoff events. This is a graph display of about a 1-month time frame from our DUMIS 1 station. And each row represents a different parameter. So we can view the level that the instrumentation has taken, and the blue triangles represent the sample events. This particular station also has a rain gauge, so we're able to view the rainfall amounts there, as well as the flow that we just previously calculated. When you zoom into a single event, it shows you the volume for that one runoff event. In this case, this is about a 12-hour time frame, and it's about 751,000 gallons of runoff. As Lee had mentioned before about the blue triangles, that represents each time the sampler took up liquid. So this represents one runoff event and would be one water sample that we send to the lab. The data from Flowlink can also be exported into Excel. And when it's done in Excel, it's reported in 5-minute time intervals, and it kind of allows you to narrow down on the time frame of an event. And you can also use Excel's formulas to calculate things such as the average flow rate or the peak flow rate. So we have these samplers that are collecting a physical water sample, which we send off to the lab for analysis, and they're also recording the measurements of the level and velocity. So now I'm going to get into how we combine those two pieces of information to calculate the loads. When we receive the results back from the lab, they're given in concentration, which is milligrams per liter or parts per million. However, we do most of our reporting in load rates, which allows for a more uniform comparison between sites. And the parameters that we look at are nitrite plus nitrate, total nitrogen, soluble reactive phosphorus, total phosphorus, total suspended solids, as well as potassium. So in order to get the load, which is the mass divided by a particular area, we have to implement a series of conversions. And we start by taking the flow volume that we have in Flowlink and converting that from gallons to liters. And then we multiply that volume by the concentration, which is the number that is given to us from the lab. And that'll give us the mass in milligrams. Then we use a conversion factor to convert to either kilograms or pounds. And then the last thing to get it over to load would be to divide by the area of the field. So if you're using kilograms, you'll divide by hectares, or if you're using pounds, you'll divide by acres to get the load of a particular nutrient from a single runoff event in kilograms per hectare or pounds per acre. So this is how we obtain all this information that we're collecting from the samplers and how we transform it into a usable format.
Thanks so much, Pearl, for your time and speaking with us today. Pearl plays a huge role in the Arkansas Discovery Farm program and even helps me out in the soil health area. And so next up we have Dr. Mike Daniels, and he's going to talk to us a little bit about interpreting that data and applying it. What does it really mean on the farm? What does it mean to our producers and to the Environmental Protection Agency? And so I'll just turn it over to Mike Daniels now. So Mike.
Thanks, Matt. I had Lee and Pearl have been talking about how we collect water quality data on farm. We think it's very important to show you the science that we use, and then the technology that we use is the state-of-the-art automated sampling. And it's more than just collecting the sample. There's a lot of work that goes into it to get the data in a usable format that then we can use to compare to how much fertilizer we applied in terms of how much nutrients is running off, or we can calculate soil erosion in terms of the amount lost per acre. And so it was very important that we show you this science, to show you the links that we go to and the quality control that we go to try to get the best data that we can. Edge of field monitoring is not perfect, but it does give us a lot of good information, but it does take a lot of work. Not only does Pearl and Lee and Mike Frialdenhoven provide this on row crop farms, but Larry Berry also provides this on livestock farms up at Fayetteville, and we work together to solve issues and handle data. So we've got a very good team, but obviously we could not do this on Discovery Farms without their help and without their support. And they're the ones that run the Discovery Farm on a day-to-day operation. Now, I want to talk a little bit about interpreting the data. Once we get the data back, then Andrew Sharpley and myself, we sit down and we go through the data and we try to decide what's going on in terms of what we're seeing. And we get a lot of help from that from Matt Fryer and Bill Robertson, because the agronomic management is important to understanding this data. One of the first things that Steve wanted to look at was irrigation, and we noticed when we collected water from our flumes in irrigation that we had a little bit cloudier, more turbid water coming out of the rainfall, as you'll see on your screen, and the water coming from irrigation was clearer. And so we thought maybe visually we was seeing a difference. And quite honestly, when we got the data back and started looking at it, we did notice that we're losing more sediment and more phosphorus in rainfall events than we do in irrigation events. And that's important to know. We have looked at irrigation. How we irrigate is important, and we can help reduce nutrients by using certain techniques for applying the water. The other thing that Steve wanted to look at was cover crops, and so we did take a look at cover crops. we know that cover crops can provide ground cover in the winter, and that can cut down on erosion. And that's what our data has shown, that we've been able to cut down on erosion in the winter time with cover crops. It also has reduced the concentration of nitrates in the runoff water with cover crops. But we also have found that we're unclear about the phosphorus. In fact, in some cases, we see a little bit more phosphorus running off in the spring with cover crops, and we're working on trying to explain that presently. One of the things that we're able to do then when we collect this type of data is that we can plot out the losses of nitrogen and phosphorus for every event. And that gives us some idea about when these events are occurring and how important those events are to what we're doing. And the slide that you're seeing right now, the reason we put this up there is that we had one event that just dominated the nitrogen loss. It was right after we applied the nitrogen fertilizer. Even though it was knifed into the ground, we got a 5-inch rainfall over from July 2nd to July 5th. And even though the losses weren't big, the point of this slide is that over 80% of the nitrogen loss came from that one storm event. This makes it difficult for us to understand. We know how to manage and control irrigation. We don't always know how to best manage for these large rainfall events that we seem to be getting more and more of. So we have found that this is a good way of working and finding out what's going on throughout the season and where we may need to pinpoint further management. The other thing that we found in this process is that we can relate back then these losses from planting to growing season back to the amount of fertilizer that we have applied. And across on Steve's farm in DeShay County, what we have found is that we're losing about 3% of the nitrogen that we apply as fertilizer and about 4% of the phosphorus as we apply as fertilizer. So when you compare that, we're very efficient. 95% of the fertilizer is staying in the field for crop use. And we think there's a couple reasons for that. First is Steve's management. Steve does not put fertilizer out until he knows he has a stand. And once he has a stand, then he knifes his nitrogen in. This actually is a liquid form of nitrogen that he knifes directly into the soil, so it's not available or as available to run off. Phosphorus he does broadcast, but phosphorus will bind very quickly with the soil. And we don't see that a problem. And so his management really affects and is really suited for not losing very many nutrients. But I think the other thing that we find is that in irrigation, we're adding and trickling that water down the rows very slowly. And these are long, flat rows, sometimes a half-mile wide. I mean long with a very little slope. And we find that we don't generate enough energy in that water to pick a lot of things up and carry out of the field. Rainfall, on the other hand, we can get particle detachment. We fill those furrows up almost immediately from top to bottom of the field, and we can get greater energy to carry things off. One thing we have found in looking at these fields for 5 years and combining all the data is that we have found that as the amount of runoff, cumulative runoff increases, so does the load. And so it's not always about the source or how much fertilizer we put out. It's also about that field's properties that control transport. And so if we can find ways to reduce runoff, and you're going to hear from Matt Fryer and Bill Robertson how we're manipulating soils to increase infiltration rate through cover crops and other things. If we can reduce that runoff, then we got a good chance of reducing nutrients too. With that, I will turn it back over to Matt Fryer.
Thanks, Dr. Daniels. We appreciate your time. Next up, we have Mike Hamilton. He is the irrigation specialist for University of Arkansas System Division of Agriculture, and he really works with farmers and county agents and trains them on how to use moisture sensors, how to become more efficient at irrigation. And so I'll let Mike tell you more about that. So Mike.
Thank you, Matt. I appreciate that introduction. I appreciate y'all tuning in today to our virtual field day. And I'm going to talk about irrigation efficiency that Mike asked me to talk about and mention soil moisture sensors here in just a moment. But the first thing that we like to look at when we're looking at irrigation is the actual flow that we're putting into our design. That's how we can put a field like this behind us. That's how we can put that in an efficient form, because we're getting the water broadcast across that whole field uniformly so that we're not running a whole lot of excess tailwater off. If you look at your screen, you can see these different measurements here, and you've got to have full flow coming out of that flow meter whenever you're measuring it. If not, it's not giving us an accurate reading. So if you're using poly pipe, you can pull that up a little bit to get full flow. You can put your hand over it to restrict the flow, or like in the top left corner, you could use an elbow that will actually, lift that up for you so that you can get full flow coming out of that. Now, a flow meter will give us plus or minus 3 to 5% accuracy. So that's very safe whenever we're putting it in our system. But you can even use a plumb bob. I'm okay with you taking a plumb bob out there on the discharge pipe and measuring that flow coming out of that well. You'll get plus or minus 10% whenever you're using that. And we build the safety in these designs very good so that we're plenty good there. You can even go from an alfalfa valve with the water coming straight out of it and get a flow that is okay to put in this program. So we always want to start with the flow. Well, why is that flow important? That flow is important because I can take a 7/16 hole and get 3.5 gallons a minute, or I can take a 5/8 hole and get 3.5 gallons a minute. So the same size hole, different size holes, I can get the same amount of water depending on the pressure that I have at that hole. And then I can get double the volume out of each hole. That 5/8, I can get 3.5. I can get over 8 gallons a minute out of that same hole if my pressure is higher. So it makes a whole lot of difference. So how do I measure that? Well, we used to use the faucet program, and that faucet program, we had to go measure everything out there. In this next slide, you'll see it's basically like an Excel spreadsheet that we have the length of the row, the length of the poly pipe, and when it changed it throughout there, we had to manually enter that into the program so that we would know where those changes was. We'd also have to manually put in at each point where the elevation changed in there. Now, we could put the start and the finish and then interpolate the data between, but the more elevation changes in there, the harder it was to put because we had to do everything manually. Well, since the faucet program, we started using Pipe Planner. In this Pipe Planner program, we can actually go in there and use Google Earth to draw our map, draw the field boundaries, and it knows the length of the furrow from the start when it changes here in the middle and then gets longer again. It knows that length for the whole run of that poly pipe. It will also let us break it into multiple sets. So click one time and you can see that we have the first set there of poly pipe, and then when we click twice more, we have the supply tubing and then the second set that we have out there, and it knows the measurements of each and every one of them. We can also upload a shape file in here that will give us elevation, and it isn't interpolating, it's the whole run of that poly pipe that we can import into the program, and that changes the whole ball game whenever we're looking at irrigation efficiency. Now we know the length of every furrow and the elevation that changes as it goes on there. So when we break it into two sets, you can see this one that is two 18-hour sets. That's a 36-hour set if we run it one time. But I like getting the water on and off faster, so we break it up into two 18-hour sets. That's still 36 hours. It's still 36 hours total, but instead of 36 running through the same field, keeping it saturated, we can do it in less time, each set separately, and actually get it watered out much quicker. Another reason that we like doing it into multiple sets like that is Mike mentioned the water running off the field. That water running off the field is very important to us, but so is the amount of water we're putting on the field. We want to make sure that's getting in the field, in the profile. So that 18-hour set, if it's done in 9 hours, then we knew we put on half the amount of water that we're wanting to put out initially. So we know that we've got to do something to change that, whether it's incorporate a cover crop or use a surge valve in that system so we get more water in there. Now, the elevation feature and the difference in faucet versus pipe planner is now pipe planner actually gives us where to put an elevation incline like you see on the screen here in your design. It'll tell you to put it at 75 foot, 218. It'll tell you where to put it down there. I've got a lot of folks that'll use a jack like this, and I'm okay with them, but a lot of times that'll push down into the soil when that runs water and gets saturated around it. So that incline may be a little less the next time we irrigate. And I don't like a big gap underneath there because that tends to stretch the pipe. I like to go over it and straight down and hang down so that I don't have any stretching in my tubing. I have other growers that'll actually put soil out there, like you see in the next slide. They mount it up to the height that Pipe Planner recommends. I've even got growers that'll leave it there from year to year and farm around it, especially growers that don't have rice in the rotation, and they can leave that there, and whether they're growing corn, cotton, grain sorghum, or soybeans, they just farm around it, and they've got their incline built in, and they do it smooth enough where they can mow over it and not have a problem out there. I've got other growers that'll put everything they got in the back of the pickup truck to make these inclines. The problem with that is when you go to build another incline, you got to go get another pickup truck full of stuff. The way I like is, and the way a lot of growers have started doing here lately, are building their own inclines so that they know exactly what they're doing, and there's no movement of this particular incline. It's getting it up to 2.5, and then it's transitioning back down. There's no slack in that poly pipe, so it'll stretch, and that's a really good design. So why do I want to put these inclines in there? You want to use a half a barrel? You can. That's fine. You could put in the program that you want to put a half a barrel, which is 1 foot incline. But a lot of times I've seen that squirt out from underneath that incline, and then your elevation is gone, so it's just chugging on down to the bottom. So you'll see in this next slide, I can put 1 over to the right of the screen. I can put 1 as my max pressure, and I got to put 15 half barrels in there. But the next screen, I put 2.5 as my max, and now I only have to put 4. Well, I would much rather put and take up 4 as opposed to putting 15 or so out there. I've got a grower I had dinner with last night here in town, and he put 52 half barrels under his run. And the system that we designed for him this year only called for 7 of these 2.5 foot inclines. He had a 16-foot fall from his riser to the bottom of the pipe. Well, that's amazing. That's a lot of incline. And he was tickled to death that he put 7 instead of 52 half barrels. Another thing that we like doing is leaving the poly pipe open-ended at the bottom. And I see a lot of growers around doing that, and I love that we're moving to that because we actually don't give that poly pipe a reason to burst at the bottom. It'll just trickle a little bit out if our elevation's not right. Some people even use this next slide, use a elbow open-ended, so whenever that height that pipe planner tells you to build it, if it exceeds that, it'll just trickle some water out the bottom. And I would much rather do that and then fix my elevation upstream as opposed to blowing my poly pipe. Next one. So you do that, you'll have a good design in your soybean system. And now I want to mention soil moisture sensors. So go to the next slide, please. I have a lot of growers over the years that ask me, how did my dry land beat my irrigated? Well, there's a difference in irrigation versus watering. We really want to get into irrigating our crop. Next slide, please. If you look at the crop curve here, you'll see the water, just like Lee mentioned earlier, on a bell curve. There it is in soybeans. The next one, I believe, is corn. Then we have milo, and then we have cotton coming in here, where we have the water use from beginning to end. Well, you see that during the peak demand of water is during the reproductive stage. So next slide. And in soybeans, we typically use 65% of the total water just through the R1 through R6 stage. Next slide. As a general rule, crops obtain about 40% of their total water requirements from the top 25% of the rooting zone, and 70% of the water for the whole season in the top 50% of the rooting zone. We also got to take into account the soil profile, the soil series out there, compaction, and a whole lot of other things we've got to look at whenever we're looking at soybean irrigation and cotton irrigation. But if we want to get our efficiency right, go to the next slide, please. We want to put these soil moisture sensors in so that we can have them at the various depths to tell us exactly where our roots are using water, how much water our plant is using. Not an average, but how much our plant is using. And that's why those soil moisture sensors are so important. And we also have specialists that you can call in your county agents, your NRCS personnel that can help you interpolate what these numbers mean and help you when to trigger irrigation and give you a good idea of how much soil water holding capacity your field has and how much water you have in the soil so you can schedule irrigations properly. With that, I'll hang it up and thank you all for watching.
Thanks, Mike. We greatly appreciate your time. And something I'd like to talk about now is a few terms that you've heard us mention: soil health and cover crops. And we have a diverse audience possibly, and not everybody may know what those two terms are. And so, what is a cover crop? What is soil health? And so a cover crop in the Arkansas row crop system, it basically is a winter annual plant that's planted in the off season of the cash crop. Cash crop is what's planted like soybeans or corn, that's planted to be harvested for profit. But a cover crop is planted there in the off season for many benefits, and there's many goals that can be achieved with cover crops, and we'll talk about those in a minute. But next I want to define soil health. USDA Natural Resource Conservation Service defines soil health as the continued capacity of a soil to function as a vital living ecosystem that sustains plants, animals, and humans. And so, that's kind of broad. We use our soils for different things. We use our soils to build on. We use our soils to grow different crops. And so that can really change the definition of soil health depending on what you're using the soil for. And so soil health is really broad and very encompassing in nature, and so it's not easily defined, and it can be hard to study and quantify. But the benefits that some of our producers are seeing is the benefits are pretty easily observable, and so we're going to talk about those shortly. But back to soil health, really when you look at the study of soil, you have three main areas: the biological, chemical, and physical properties of soil. Biological area would consist of organic matter, roots, biological activity like microorganisms and earthworms. The chemical area would be soil pH, nutrient availability, cation exchange capacity. And then when you talk about physical properties of soil, you're talking about soil structure and how well the soil holds together. You're talking about infiltration, how quickly does the soil allow water to infiltrate down the profile. And then you're also talking about how well the soil holds water over time. And so soil health is really right in the middle of that, and if you leave out any one of those main areas, you're really not talking about soil health in general. And so in our next slide, you'll see that when you go to implement soil health, in a nutshell, it's not tilling the soil, and it's using a cover crop in the off season. And so the goal is to not disturb the soil, not rip it up and tear it up, and then to also keep it covered and then keep living roots growing in the soil for as many months out of the year as possible. And so there's many benefits that you can achieve with these practices, like infiltration, weed control. When we keep the soil covered and shaded, it reduces weed seed germination. Those roots and the increased biological activity from keeping the soil cooler increases infiltration rates. When you have a bunch of earthworms making a bunch of channels, it allows water to infiltrate faster. You can also add nitrogen to the soil if you're using a legume cover crop. And then of course we're preventing erosion when we're keeping the soil covered, and we're preventing erosion from water and wind. And so some of those improvements are really a long-term goal-based, and they can vary from field to field. And so really there's more research that's needed to really quantify, put a number to those exact changes and what we can expect to see with implementing these practices. But there have been some preliminary data here in Arkansas, and we're highlighting Steve Stevens farms in Rower, and when you look at typical infiltration rates of silt loam or sandy loam soils, you see a half to an inch and a quarter inch an hour of water infiltration. Well, some of Steve's fields are a little bit above that, 1.75, but some of his fields where he's had cover crops on, he's up to 4 to 5 inches an hour. And so that's a big deal when you talk about capturing rainfall, reducing irrigation costs and pumping costs. I used to think that the biological soil activity, you can't really correlate that to crop growth or yield, or it doesn't mean much to us, but it actually does, because when you have increased biological activity, increased earthworm channels, it really helps with that infiltration, and that can help with the bottom line. And so, you know, profitability is the bottom line, and that's really more of a short-term benefit of using these practices, no-till and cover crops. You know, some of our producers are showing more sustained profits across time, where their yields aren't as volatile, you know, over the years compared to when they were doing a conventional till, no cover crop system. And also, they're spending less money. They're saving money on tillage. They're saving money on equipment costs, wear and tear, and they're not paying labor to run that equipment all the time. And then, of course, weed control savings, where they're having, in a lot of cases, they're reducing their herbicide applications because they're keeping the ground covered and they're not having as many weeds germinate. And so, you know, all these benefits are very achievable, but in some cases, it's hard to implement these practices, you know, depending on what crop is in the rotation. It can be difficult. It can be easier for some farms than others, but these changes are very beneficial, but again, it's hard to implement at times, and so because it really changes the whole production system. So instead of a farmer trying to manage one crop from spring to fall, he's also managing two crops from throughout the year, and so he's got to worry about terminating the cover crop. He's got to worry about getting the cover crop planted after he gets his cash crop harvested, and so it really increases the management demand on these producers. And so it's important to have a goal in mind, because, you know, you can really run into problems if you don't have a goal and you're just blindly trying to implement these practices. We don't recommend planting a legume cover crop, dominated cover crop, in front of a legume cash crop like soybeans, and we don't recommend planting a grass cash crop that's, you know, dominated by grass species in front of a grass crop like corn or rice. And so, really having a goal in mind and working with your county agents and your specialists to help you get off to the right foot is important. And so, in a nutshell, that's really soil health and cover crops. And I wanted to touch on soil potassium and runoff. You know, in the first segment, we talked a lot about nitrogen and phosphorus measurements in runoff water. But something that the Arkansas Discovery Farms is doing through some funding from the Arkansas Fertilizer Tonnage Program is they're measuring potassium in the runoff water. And so that's really not an environmental issue, but it's more of a budget issue. And so, you know, if our producers are applying potassium fertilizer and half of it's running off, then you know, that's a big deal. But that's not the case, is what we're finding. And so we were interested to really quantify this. We're interested in looking at native soil potassium levels, as well as cover crop use, on the effects of potassium in runoff water. And so, just like Lee showed you earlier, they're taking water and samples, and we're taking soil samples in the field, and we're sending those off to the lab to be analyzed. And so, when we're looking at the native soil potassium levels, we're taking fields like you see here in the picture, and we're dividing the field in 1 acre grids and taking soil samples in that grid. At each grid, and then we're sending them to the lab, getting our numbers back, and then Pearl enters those numbers into the software mapping program, and it maps, gives us a map like you see here, and then we enter our soil test levels from the University of Arkansas that gives us a color code based on our different potassium levels. And so that really helps us to correlate, you know, the soil native potassium levels to what we're seeing in runoff. And so, you know, just like nitrogen and phosphorus, potassium runoff is variable, and it can vary from field to field, and so we're still got a lot of work to do there. And again, this is a budget implication and not environmental. And so all of this is just 1 year of data, and we're very preliminary results. What we've found is that, just like for nitrogen and phosphorus, our producers are over 90% efficient at using what they apply. And so, you know, they're using over 90% of what they apply, and so it's either being removed in the crop or it's staying in the field. It's not running off in the water. And so, just to sum things up, that's pretty much kind of what I wanted to talk about. You know, one of the benefits of this virtual field day is questions. You can send in questions live, and so to go ahead and use the chat option on your screen and send in questions, and we'll have our specialists answer those here in a little bit. But right now, I'd like to turn it over to Dr. Bill Robertson. He's our cotton agronomist for University of Arkansas System Division of Agriculture, and he's going to talk about implementing these practices, what they're seeing in cotton, and also the sustainability of cotton production. So, Dr. Robertson?
Okay, thanks, Matt. This has been 61 years in the making to get to this, my very first virtual field day, but you can teach old dogs new tricks. But to start with the Discovery Farms, there's a lot of times people ask me, well, what are y'all discovering? And so, like Mike Hamilton talked about doing different irrigation practices. A lot of fields are split in half, where we can do their standard irrigation practice on one side and then try the pipe planter on the other side. We can look at different nitrogen sources, different timings, to discover not only what it does to yield in the field, but discover what leaves the field. So there's a lot of things we look at. And then I come along. I ask them, can we incorporate practices that improve soil health into this program? So on one side of the field, we're doing the farming just the way the producer has always farmed. On the other side, we're incorporating two basic practices to improve soil health, and Matt talked about those a while ago. The incorporation of the use of cover crops and then reduction of tillage. So with our cover crops, for me, the main thing we're wanting to do is feed the soil microbes. And the interaction between feeding the soil microbes with live plants and living plant tissue out there, and the interaction that the microbes have on soil structure, tends to help improve our soil structure. And then when we reduce tillage, we don't destroy that soil structure, so we build it over time. So it's that two-step process. And then, I'm here with kind of the tools of my trade as an agronomist and working on soil health. How do we know if we're improving soil health if we're not looking at it? So I use a shovel a lot, and I use a soil probe a lot to see what's going on. The shovel, if you go out with a shovel, and if you have good soil health, you're going to see earthworms. Earthworms are very good indicators of a healthy soil. So whether you're in a pasture, a hayfield, your garden, your flower bed, even in row crops, if you see earthworms out there, that's an indication that you have very healthy soil, and it gives you kind of a goal to go to. But when we look at adopting practices to improve soil health, we run into a lot of hurdles, and we see on this first slide that the perception, the peer pressure, and kind of human nature of being hesitant to look at those new practices because a lot of times they don't look right. If we look at the next slide, we can see some of the different things that are going on. And a lot of times we ask, okay, who's the best producer? When I was growing up, we'd drive through the country. I grew up outside of Lubbock, Texas, but anybody with straight rows and clean fields were a good farmer. And we look at this now, on the one side we've got straight rows and clean field, on the other side we've got the cover crop. When we grow cover crops, even though there's a lot of advantages, it doesn't look right. So we have to do not only education and demonstrate to the producer that these practices work, but also we need to talk to the landlords and the lending institutions and all that, because when we look at that picture on the left, it looks like a grown-up mess. So when we look at other hurdles to adoption, a lot of times, I really get locked into this too. Sometimes I don't feel like I've got so many things to do. I don't feel like I have time to learn new things. On this next slide, I feel kind of like these cavemen. That I'm so busy, I'm pulling this wagon, I'm doing the best I can. I don't have time to talk to that guy with this new idea about round wheels for a wagon. I'm going to keep doing what I'm doing. So there's a lot of benefits to stepping back and looking at new things and trying those. But certainly when we get into something like this, there's always room for more research, and certainly we find that more research is needed on this. When we look at this slide here on the bottom left, Steve is out checking his stand, and the scene back behind is we're terminating and planting on the same day. When we talk to our entomologists want us to terminate 4 weeks in front of the planter to reduce the chances of seeing a green bridge. And green bridge is when we have insect pests leaving the cover crop onto our cash crop as the cover crop is dying and the cash crop is coming on. Our weed scientists want us to terminate the cover crop 10 days to 14 days in front, especially if it's straight cereal rye to plant green. But like on this slide that Steve was at, we see that we're terminating and planting on the same day. And for a producer, when we have a lot of 4,000, 5,000 acres of cotton or beans or whatever we have, sometimes that gives us a lot of flexibility. Now as we go on, when we split the fields the way we do with the Discovery Farm, that gives us an opportunity to see a lot of different things. And we go out there, and I like to bring the producer out and have them come out and look at some of those. The previous slide, Vonda, Steve Stevens' daughter, was riding her horse on the turn road up an elevated height. You could see a lot of things. I can see a lot of things up high that I can't see walking the turn row. And she saw a big difference between the cover crop and no cover. That was a period of dry weather. Our rainfall, we had much improved water infiltration, and that's just a function of soil moisture. When we look at the next slide, we see I had Steve go out right after a big rain, 3.5 inches of rain. It was probably about 4 hours afterwards, but there was hardly any runoff come from the side that was no-till with a cover crop. When we looked at even where we had a cover crop and a stale seed bed, the little bit of tillage we did after the picker compacted the soil, and we had much less water infiltration and much greater runoff. And there's a lot of other visual things out there. When I walk across with a soil probe this year, in the fields where we split in half, the side with cover crop, the soil felt soft. It was easy to put the soil probe in. On the other side, it felt hard, is almost like a pavement, and we couldn't hardly get the cover crop, the soil probe in. Now when we look at what's going on with in the field, when we don't do tillage, a lot of times our beds get a little flat. We run a Prorunner Plow that just parts the cover crop, and we do it in a way not to expose any soil, because when we expose soil, usually we have opportunity for pigweed control. Now as we move on and look at, there's our Prorunner Plow that I was just talking about. If we move on and look at what we see, there's the Prorunner Plow, no exposed soil. Where Steve pulled his beds, you see it's exposed soil. But when we go on, what does a healthy soil look like? We see different things. A good indication of this is with this slide with the irrigation running down the row. And the image on the right is from Steve's. The water doesn't soak all the way up to the top of the row. I'll go out with this soil probe. I'll hit dry soil about 6 inches deep. On the other side with a cover crop, water soaks all the way up to the top of the beds. We get very good water infiltration. A lot of times in his standard side, we're farming really about this top 6 inches. On the other side, even in our soils, we're doing a very good job of farming the top 2 foot. The U.S. cotton industry has goals set for sustainability, and sustainability is good. I've talked about the agronomic parts, and now then, why is sustainability important? Because the brands and retailers are really pushing for sustainability. There are a lot of companies, the Walmarts and the Tysons, have pretty lofty goals on being more green, more sustainable, and their measuring stick for this is reduction in greenhouse gas emissions. There's a lot of things that big companies can do in-house to do that, but it also goes back to the raw goods that they produce, and the people that source cotton are really looking for fiber that they can source that's responsibly produced, that's sustainably produced. And these are an illustration of the goals that the U.S. cotton industry has. When we look at what we've done at Steve's, we've worked with several people. I've worked with the Field to Market Alliance for Sustainable Agriculture, and one of their tools is a Fieldprint Calculator. And Steve talked about earlier, and I hope you were able to catch the first virtual field day today. He talked about we recorded everything that he did. So to go into the Fieldprint Calculator, basically we look at the size of the tractor, the size of the plow, the amount of fertilizer, the amount of pesticide, everything goes into this. And we look at the environmental footprint associated with that. We look at several metrics. We look at land use, or basically the yield. We look at soil conservation, that's air and wind erosion. We look at soil carbon. We look at irrigation water use efficiency. We look at greenhouse gas emissions, we look at energy use, and we even look at edge of field water quality, which is associated with this project. Now when we look on the right side of this slide, we see that one side is for his tilled side with no cover crop. Look at the purple shaded area, a pretty good sized area. Compare that to the shaded area on the left. That's the environmental footprint where we use no-till with a cover crop. So a very big difference in the environmental footprint between just the two practices. And the main thing that we did was incorporate the use of a cover crop and reduce tillage. So when we look at things like this, the supply chain is wanting us to be more sustainable. But Steve was talking about today, you know, as a farmer, the main thing we're worried about, or the main thing that we're concentrating on, is making a living. Things have to pay. We have to farm first, and then when we do these other improvements, we add them in to become better. And that's one of the things that the industry is looking for toward continuous improvement. But the big thing for Steve, when we look at those practices that tend to reduce his production cost and tend to reduce our environmental footprint, a lot of times those make us more profitable. And as Steve talked about today, on the side where the field that we split, we were able to produce cotton a nickel a pound cheaper on the side with no-till and cover crop compared to his standard tillage practice with no cover crop. So when we tie these together, there are things out there that will make us greener, more sustainable. There are things out there that will make us more profit. And those are the things that we need to line up, because those are the things that our supply chain needs and wants, and we need to do those so that we can ensure that U.S. cotton is on the shopping list for companies that want to source sustainably produced fibers. So Matt, that kind of completes my section, and I'll turn it back over to you.
Thanks, Dr. Robertson. So now we'll answer any questions that you may have. We'll have our expert panelists come up and we'll film this and answer any live questions. So I'm just going to walk over there now. And I guess one of the first questions is, you know, it may be a loaded question, but I think Bill might be a good candidate to answer here, is what's a good cover crop recommendation? And that's kind of a loaded and vague.
Well, you know, a good cover crop recommendation is almost like a snowflake. One size does not fit all, or a cookie cutter. A lot of producers I work with that have never grown a cover crop, a lot of times we try to keep it simple and start simple. So for a crop like cotton or soybeans, a cereal rye cover crop works really good. You know, a lot of times when we look at people talking about cereal rye as a cover crop, they say cereal rye is the cover crop with training wheels. And so it's easy to establish. We can fly it on, we can spread it on, we can drill it, and it's easy, and we get good growth. And then also it's easy to terminate. Some of our cover crops are difficult to terminate. If we don't plant them at the right time, we don't get the winter kill, and we've got a mess. So cover crop, so cereal rye is easy to start and easy to terminate, and a good thing to get your feet wet, and then you can expand into multiple species and find a mix that works best for you, because what works good for me is probably not going to work best for you.
Yeah. And also I think I'd echo what you say too, is that we should talk to your county agents before you pick a good cover crop. So we have time for one more question. It was a question on irrigation, so Micah, maybe for you. How do you irrigate in a cover crop no-till system relative to
well, the first thing I do is I run the pipe planter on the field so that I know an idea of how much water I'm actually putting on the field, so that I have a starting point. And I know that with a cover crop I should be putting on more than I am in a normal situation, because I should increase my infiltration. So start off with pipe planter and get a base, and then use the cover crop so that you know if you're getting more or less in the profile.
All right, thanks. Good answer. That's all the time we have for today. We just want to thank our funders, USDA Natural Resource Conservation Service, for funding this project. All the University of Arkansas System Division of Ag staff for doing the behind-the-scenes production on this. It's quite extensive, and we want to thank the Dabb's Farm for allowing us to use this location, because and we tried to use the rower location at Steve Stevens' farm. The Wi-Fi signal wasn't strong enough to support. So we just want to thank you for joining. We hope it was beneficial, and we hope you have a good day.